And I just want to right away let everyone know that this program is going to be recorded for other people to be able to watch. Something just to be aware of, especially if you don't want to appear on a recording, is just to keep your camera off. And for those of you who don't know me, I'm Samantha Russell Bloom-Koenig. I'm the Chief Naturalist at the Eagle River Nature Center, and you've made it to our astronomy program. Couple things coming up. First, we are no longer doing our outdoor information desk. It's just gotten too cold, and Colin and Timothy are finding other things to do. But the good news is we just installed a credit card reader parking fee. So we're excited to be able to bring that to you guys. Other things coming up, especially since this is an astronomy crowd, on November 20th, I believe that's that Friday, Omega Smith is going to be talking about oceans on other planets. So that information is all on our website, and you can register for that as soon as you're done with this program if you'd like. The final thing, I'm just going to send everybody a link, is unfortunately we were not able to have our annual fundraiser this year, our annual auction. And so Asta's asked me at the beginning of every program just to make a mention, if you feel so inclined to keep supporting programs like this and the amazing trails, if you could just donate at the link in the chat box. I'm so sorry about my dog. With that, as we go through tonight's presentation, Travis has asked that you either use the hand raising feature or use the chat box to ask questions. He'll be keeping an eye on both, and if for some reason I notice he's not seeing anything, I'll be sure to chime in. And yeah, we're glad you made it. So with that, I'm going to turn it over to you, Travis.
Okay, thank you, Samantha. Hopefully everyone can hear me okay. So, wow, hello from Texas. So thank you for coming. Hi everyone, my name is Travis Rector, and I'm a professor of physics and astronomy at the University of Alaska Anchorage, here in Anchorage. And so I'm a professional astronomer, and Eagle River Nature Center's invited me to come talk with you today. And what I'm going to do for my talk today is talk about the terrestrial planets. So as Samantha mentioned, I do have the chat window open as well as the participants. So if you have a question at any time, please feel free to raise your hand or to type in a question in chat. And when it's a time that's appropriate, I will pause for a second to answer your question. So let's go ahead and get started. So what I'm going to do is I'm going to talk about the terrestrial planets in our solar system. And by terrestrial planets, I mean the 4 planets in our inner solar system of Mercury, Venus, Earth, and Mars. And in the conversation, I'm also going to talk about our moon, because even though it's not a planet, it's orbiting around us instead of the sun, it is an object that is in many ways very similar to the terrestrial planets. And so what I'm going to do is I'm going to talk about each of the terrestrial planets and how the terrestrial planet ended up different, how each planet ended up differently from the others. So to start off with, I have a table here that lists some information about each of the terrestrial planets. It has the radius of the planet relative to the Earth, its mass as well, and then also the density of the planet, which is just simply the mass divided by the volume. And I'll point out a couple trends. First off, notice that Venus is a planet that is very similar to the Earth in size and mass. It's just a little bit smaller in radius and also slightly less massive. And then if we look at Mars and Mercury, notice that those are considerably smaller than the Earth. Mars is about half the diameter of the Earth, and both Mars and Mercury are about 10% or less the mass of the Earth. And finally, I'll point out that the scientists often use the density of a planet to learn something about it. And you'll notice that Mercury, Venus, and Earth have densities that are very similar to each other, whereas Mars and the Moon are significantly less dense. And this is a clue that tells us that Mars and the Moon have a different history as to how they formed compared with Mercury, Venus, and the Earth. Now, another thing that we'll talk about is the atmospheres of these objects. And so this chart right here shows what the atmospheres are like for each of these. And first off, we'll point out that Mercury and the Moon don't have, pretty much don't have any atmosphere at all. And so that just leaves us with Venus, Earth, and Mars. Now, Venus and Mars have atmospheres that are made almost entirely of carbon dioxide gas. And you've probably heard about carbon dioxide in conversations about climate change here on Earth. And so I'll talk a little bit about that. Now, the other thing I want you to notice is that the Earth has an atmosphere that's very different than Venus and Mars. It's made mostly of nitrogen and oxygen. And so a good question to ask is well, gee, why did Earth end up with a different kind of atmosphere than Venus and Mars? And I'll talk about that too. And finally here, I'll just point out that Venus has a very thick and heavy atmosphere compared to the Earth. And likewise, Mars has a very thin atmosphere compared to the Earth. The atmosphere of Venus is about 90 times thicker than the Earth, whereas Venus is a tiny fraction. And so what I want to do is talk about how each of these planets ended up the way they are. So first thing we're going to do is we're going to go inside the terrestrial planets and talk about what's going on in there. And so we'll start here with the picture of the Earth. And so the Earth has an inner core that is very hot and is solid. And then outside of it is an outer core that's not quite as hot, but it is liquid. And the reason why it is liquid is because it's hot enough that the material in there melted. Now the inner core is even hotter, but the intense pressure and weight keeps it in the form of a solid. And then the outermost layer here is a layer that's called the crust. And then above that is the atmosphere. So how do we know this? Since we can't drill inside the Earth or any of the terrestrial planets, how can we know what's on the inside? Well, the way we know what's going on the inside of the terrestrial planets is actually from earthquakes. So what happens is whenever an earthquake occurs somewhere on the Earth in what's called the epicenter, it sends out these waves throughout the interior of the Earth that are called P and S waves. And these P and S waves can, as they travel through the Earth, they're affected by the inner and outer core, and that changes the way the waves look. And so that's how we can actually figure out that the interior of the Earth is molten. Now, the outermost layer of a planet is either called the crust or the lithosphere. And the lithosphere is basically the outermost layer. And because it is cooler than the interior, it can actually break if it gets moved around. And I have a picture here of silly putty because as a kid, if you ever played with silly putty, you may know that silly putty is a material that when it is warmer, it moves around more easily, and when it's colder, it is more brittle. And in particular, if you take silly putty and you move it quickly, it'll break, it'll crack. And so that's what happens to the surface of the Earth as well. If there's pressure on it and it moves, then it can crack, and that can cause earthquakes. So, so what is the big difference between the terrestrial planets? Has to do with the size of the planet. So what happens is when the planets formed, the interior of the planets was very hot, and over time, the planets have cooled by radiating their heat out into space. Now, the amount of heat that's inside a planet depends on the volume of the planet, and that goes by this simple equation. If you remember from your geometry class, that the volume of a sphere is given by this equation here. And all that heat has to go out through the surface of a planet, and the surface area of a planet is given by this equation here. So the volume depends on the radius of the planet cubed, whereas the area of the planet depends only on the radius squared. So what this means is that larger planets cool off more slowly than small planets. So small planets like Mars and Mercury have actually cooled off to the point where they're now completely solid inside, whereas Venus and the Earth are still molten on the inside. Now, this is important for a variety of reasons. One of the reasons it's important is volcanic activity on a planet depends on the interior being molten. So Venus and Earth are still volcanically active, whereas Mars and Mercury and the Moon are not. So just to put this in perspective, the Earth's interior has about 50 times more heat than the Moon, but only about 13 times more surface area. So what that means is it takes longer for the heat inside the Earth to get out, and so that's why it has stayed hotter for longer. Okay, we'll talk about why that's important here in a second. Now, all of the terrestrial planets have changed over time, and what we're going to do now is talk about 4 processes that can change the surface of a planet. The first is what's called impact cratering, which is just simply if an asteroid comes in and smacks the surface of the Earth or a planet really hard, it can change what the surface looks like. There's also volcanism. That is, if the interior of the planet is molten, then lava can break through the surface and flow onto it. The third is what's called plate tectonics, which is that the topmost layer of the planet can shift around. And then the fourth one is erosion. And that is, if a planet has an atmosphere, then weather conditions on the planet, like wind and water and ice, can actually change what the surface looks like too. Now, for this to happen, of course, you have to have an atmosphere. So since Mercury and the Moon don't have an atmosphere, there is no erosion on these planets. So let's talk a little bit more detail about each of these processes, and I'm going to start with volcanism. And volcanism, again, is when molten lava from the interior of the planet, which is called magma, breaks out into the surface and then flows out onto it. Now, how much lava breaks out and the effects of it depends on the lava's viscosity. And so I have a picture here of maple syrup. Maple syrup is an example of a viscous fluid. It's a fluid that doesn't move very easily. So water is an example of a low viscosity fluid. It flows easily, whereas maple syrup is a high viscosity liquid. It does not flow as easily. So high viscosity lava or thick lava can produce steep volcanoes. And so here on Earth, Mount Rainier and Mount Hood are examples of these. Mount St. Helens is as well. And so what happens is as the lava comes out, it doesn't flow very easily, and so it just piles up and makes steeper volcanoes. Now, we also have on Earth what's called mid-viscosity lava, and that produces shallower volcanoes. So if you go to the Big Island of Hawaii, Mauna Kea and Mauna Loa are example of shallow volcanoes. They're very big volcanoes, but the walls of them are not as steep as what you have for high viscosity volcanoes. And then finally, you can have low viscosity lava that is so thin that it acts just like water. So I'm going to show you some pictures of the Moon, and these are places where the Moon had low viscosity lava and it flowed out and it was nice and smooth. So here are some pictures to share with you. This is Mount St. Helens, which for those of us who are old enough to remember when it erupted in 1980, it was a massive explosion. And part of the reason why it was so massive is because there was a lava plug. That thick lava prevented it from flowing out easily, and then eventually the mountain exploded. Now, in comparison, if you look at this is a picture of Mauna Loa, which is one of the 2 large volcanoes on the Big Island of Hawaii. Now, Mauna Loa and Mauna Kea, which you can actually see there in the background off to the right, they're just giant volcanoes. They're physically huge, but the walls of them are not nearly as steep. Now, for comparison, this is a picture of the surface of one of the craters on the Moon. And what happened here is billions of years ago, when the Moon was still hot inside and it had lava, an asteroid hit the surface of the Moon, cracked the surface, and then lava was able to come out. And that lava, since it was low viscosity, flowed out and filled up this crater and gave it this nice, smooth appearance. Now, you'll also notice there's some smaller craters that later on then are from asteroid impacts that hit that location many years later. So this is an example of a lava flow on the Moon, and you can see it looks very smooth. Okay, now another thing that happens with volcanic activity is something called outgassing. And as you might guess from the name, it is the releasing of gas that's trapped inside the planet's interior. So volcanoes here on Earth continue to release the water vapor and carbon dioxide as the result of outgassing. And also, this is also true for Mars and Venus. And in fact, the way they got their atmospheres was from this gas. So an important thing that I'd like for you to know from today's talk is that Mars, Venus, and the Earth all got their atmospheres initially from the release of water vapor and carbon dioxide into the atmosphere. That's how they came about. So here's a picture of a volcano on Earth. And if you've ever been near a volcano, you can smell the gases coming out. We can't smell carbon dioxide, but there's other gases that are released like sulfur dioxide, which is that stinky, rotten egg smell that you've probably smelled if you've ever been near a volcano. Now, a question I often get is, are volcanoes responsible for the addition of carbon dioxide to our atmosphere that's causing climate change? And the answer is no. Volcanoes do release carbon dioxide, but they do it very slowly. And so compared to the release of carbon dioxide from the burning of fossil fuels, it's a very small amount. So for perspective, every year volcanoes on Earth release somewhere between 60 to 300 million tons of carbon dioxide. Now, for comparison, in the year 2019, the use of fossil fuels here on Earth released about 33,000 million tons. And so you'll notice that the fossil fuels release about 100 times more carbon dioxide than volcanoes do. And sometimes people get those numbers backwards, but volcanoes don't release nearly as much as fossil fuels do. Okay, next thing we're going to talk about is what's called impact cratering. And impact cratering is just a fancy way of saying the crater that's produced when an asteroid or a comet hits the surface of a planet. So asteroids and comets occasionally do hit a planet, and they hit at really high speeds. They can come in as fast as 200,000 miles per hour. And just the energy released from that impact can cause this giant crater. Now, the good news is that impact cratering nowadays is relatively rare. Most of the craters that we see on the moon and other places occurred billions of years ago. But there are still asteroids floating around. And one of the things that my students and I do at UAA is actually look for what are called near-Earth objects. These are asteroids that have orbits that bring them close to the Earth, and we want to find out whether or not they're actually a threat to hit us. The good news is we haven't found any that are anything we need to worry about. Now, one thing I'll mention is that larger planets get hit more often by asteroids because they have stronger gravity and they're also simply bigger. And also because they have stronger gravity, as the asteroid is falling towards the surface of the planet, the gravity speeds it up, and so it actually hits faster. And so in general, you would expect larger planets to have larger craters on them than other places. But as we'll talk about in a second, that's not actually what you see. And the reason, and it has to do with other things happening on these planets. So why does the moon have more craters than the Earth? Well, the answer is fairly simple. The moon doesn't have an atmosphere. And so here on Earth, there have been processes like plate tectonics and erosion that have pretty much wiped out evidence for most of the craters that once existed on Earth. There are still some craters that we see, but not nearly as many as the ones we see on the moon. Since the moon has no atmosphere, whenever something hits it, it creates a crater, and that crater basically stays there for nearly forever. Okay, now we do see impact craters on other places. So for example, here are two craters that occurred on the surface of Mars. And you'll notice that these two craters look quite a bit different. Notice that the crater on the left is a nice circular kind of bowl-shaped crater. And the crater on the right looks very sloppy. And also notice that there looks like a mountain or a peak at the center of the crater. And the reason why that is that the crater on the left was caused when an asteroid hit a dry part of Mars, whereas on the right picture, the asteroid hit a wet part and splashed out all this mud on the outside, and some of that material sloshed back into the crater and then sloshed up to create the peak or mountain at the center of the crater. So these craters can actually tell us quite a bit about what the surface of the planet was like where that impact occurred. So here's an example of a crater on Mars. And this is a crater that we now know was once filled with liquid water. And we know that because we strongly suspected that because if you look at this picture, you'll notice the interior looks very flat. And if you look down at the bottom part of the crater, you can actually see a creek bed where water drained out. So because of its appearance, NASA launched one of the Mars rovers named Curiosity to land in this crater. And the Mars rover then analyzed the rocks inside this crater and found evidence that, yes, indeed, this crater once was filled with liquid water. Now, the water didn't create the crater, but the water did at some point fill it up. And that water has long since gone away, but we do know that at one point there was liquid water inside this crater, which is pretty amazing to think about. Okay, and then finally related to this is the topic of plate tectonics. And plate tectonics is just simply the fact that the surface of a planet can move around. If a planet is liquid on the inside, like it is on the Earth, then you can think of the surface of the planet is the plates just floating on top of the surface, and they can move around. And this movement can cause the outer layer of the planet, which is called the lithosphere or the crust, it can cause it to shift around, and it can crack, it can stretch, it can do a bunch of different things. So here's an example of this happening on Earth. What you're seeing is a picture of the Appalachian mountain range in the eastern United States. And what you're seeing is the mountains themselves are a crumple zone that's caused by two plates colliding into each other. And then here's an example of just the opposite. What you're seeing in this picture is plate tectonics that happen on Mars, and it's two plates moving apart. And so what you're seeing in this picture here, these vertical lines that look kind of like tiger stripes, are actually stretch marks where the surface of Mars was getting pulled apart. And then finally, I just want to talk briefly about the process of erosion. So erosion is how the surface of a planet is changed if there is ice, water, or gas in the form of an atmosphere on the surface. Now, when we think of erosion, we usually think of things getting broken down, but erosion can actually build structures as well. So for example, the sand dunes over by Kincaid Park here in Anchorage are the result of the winds blowing sand up the slope and building those sand dunes. Now, an important thing to know is erosion only occurs on planets that have an atmosphere, because you need an atmosphere to have ice or water, and of course to have wind as well. Another thing that you need is the atmosphere must be moving quickly. So for that to happen, the planet has to be rotating quickly, and Earth and Mars are the only two planets that in our solar system that have atmospheres and rotate quickly. Venus has a very thick atmosphere, but it rotates very slowly, and therefore it doesn't have much wind on the surface. So there's basically no evidence for erosion on the surface of Venus. So let's talk a little bit about how each planet turned out differently from the other. And first we'll start off with the Moon and Mercury. Now, the Moon and Mercury are very small, and as a result, their interiors cooled off about 3 billion years ago. So our solar system as a whole is about 4.5 billion years old. And so for the first billion years or so, the Moon and Mercury were hot enough on the inside where they could have, they had a liquid interior and there could be volcanic activity. But by about 3 billion years ago, the interiors have cooled off and the planets have completely solidified. So we see evidence that there once was volcanic activity on the Moon and Mercury, but it was a very long time ago. Now, the Moon and Mercury also, because they're very small and have little mass, don't have enough gravity to have a significant atmosphere on them. So as a result, there is no erosion on these objects, and there's also no protection from asteroid impacts. On Mars, Venus, and Earth, our atmospheres actually protect us from small asteroid impacts. If an asteroid gets into our atmosphere, as it's flying through the atmosphere, it'll burn up and break apart. But on the Moon and Mercury, there is no atmosphere, so even the smallest asteroids will hit the surface and make a crater. So when we look at the surfaces of the Moon and Mercury, the surfaces we see are basically the result of two things: from asteroids hitting the surface and creating craters, and then also lava flows that occurred from these impacts many billions of years ago. So when we look at the surfaces, we do see evidence that there once was lava on these objects. So here's a picture of the Moon. In fact, here are two pictures of the Moon. The picture on the right shows what's called the near side of the Moon. This is what the Moon looks like as seen from Earth. And the picture on the left shows what's called the far side of the Moon. Now, the Moon orbits around the Earth in a way that it keeps one side always facing towards the Earth. So whenever you look up at the Moon, the picture on the right is the side of the Moon that you're seeing. Now, if you look on the far side of the Moon, you'll notice that it has a lot of craters on it. It has more craters than the near side. And also, if you look at the near side, you'll see these darker areas, and those are the lava flows. Those are the places where asteroids hit the surface of the Moon, cracked the surface, and lava flowed out. Now, the reason why the near side of the Moon looks different than the far side is that the crust of the Moon on the far side is thicker, and so wasn't as easily cracked by these asteroid impacts. Okay, so here are just some nice pictures showing what the surface of the Moon looks like. This was a picture taken by one of the Apollo spacecraft that flew out to the Moon in the 60s and 70s. And what I want you to notice in this picture is that the bottom half of the picture, you can see these nice, relatively smooth lava fields on the surface of the Moon. And off in the distance, you can see one of the big craters. So then this part of the Moon that we're seeing right here in the foreground is actually a younger surface because it was covered over by this lava flow, where the other part of the Moon in the background is older because it wasn't covered in lava. And here's just a nice picture showing some of the mountains that are on the surface of the Moon. So just some nice, more nice pictures showing some of the impact craters on the surface. Okay, now let's talk about Mars. Mars is a very interesting planet for a lot of reasons. You may know that Mars is of interest to scientists because it is one of the places in our solar system where we think it is possible that life might have once existed and that life might actually still be there now. Now, Mars is not as big as Venus or the Earth, but it is larger than the Moon and Mercury. Now, Mars is small enough that the interior of the planet has completely cooled and solidified. So there was a time when Mars had a molten interior and was volcanically active, but that is no longer the case. Now, Mars was more tectonically active because it was bigger than the Moon and Mercury, but not as tectonically active as Earth and Venus. Now, Mars has only 10% the mass of the Earth, so as a result, it makes it difficult for it to have a thick atmosphere. So Mars has a much thinner atmosphere than Venus or the Earth. Now, there's a lot of misconceptions about the planet Mars. Because Mars had many similarities to the Earth, people a long time ago thought that it is a place that life could potentially exist. And so this led to the idea in our popular culture of Martians and that live on Mars. And this started because in 1877, there was an Italian astronomer named Schiaparelli, And looking at Mars through his telescope, he saw these dark, what he thought were dark streaks on it, which he called canali, which is the Italian word for channels. Now, you're probably familiar with the word canal, and in English, a canal is a channel that carries water in it. And so what happened was, not several years after Schiaparelli's observations, there was an American astronomer named Percival Lowell, and also looking through his telescope, he thought he saw a lot of these canals, and he interpreted them as being irrigation dishes that were carrying water to cities on Mars. And so this picture on the left shows a drawing that Schiaparelli made of what he thought the surface of Mars looks like. Now, back in this day, they didn't have photography, so all they could do was look through the eyepiece and draw what they thought they saw. Now, Percival Lowell, was shown here in this picture on the right, looking through the eyepiece, he drew out this very elaborate map of what he thought was on Mars, cities shown as these circles, and then he thought he saw all these little channels that connected them. Now, in hindsight, looking back at this all seems rather silly because we don't see any evidence for any of this on the surface of Mars now. But because of what Schiaparelli and Percival Lowell thought they saw, that led to the idea of Martians. And so even up to the 1960s, if you ask people, do you think there's life on Mars? Many would have said, yes, they did. And so the whole idea of the Martian myth originated from these early drawings. Now, the reality of Mars is that it is a dead and dry planet. But we do see evidence that there once was liquid water on the surface. And I showed you some pictures where we could see there was places where water did flow along channels and streams and filled craters. Now, Mars has some interesting features on it. Even though Mars is not as volcanically active as the Earth or Venus, it does actually have the largest volcano in the solar system, and it's called Olympus Mons. And this volcano is no longer active because the interior of Mars has cooled off, but it was at one time a very active volcano. Mars also has a giant canyon in it called Valles Marineris. And this canyon, if it were on the United States, it would extend from Washington State down to South Carolina. That's how big it would be. So it's a huge canyon comparison. And it also has a giant crater on it called Schiaparelli crater in honor of the Italian astronomer who first noticed it. So what you're seeing in this picture right here is a modern day picture of Mars taken by one of the Viking spacecraft that was sent to Mars in 1976. And looking at this picture, you can see that there are brighter areas and darker areas that Schiaparelli could have interpreted as being these channels. On the other side of Mars, we have Valles Marineris right over here, which is this giant canyon that I talked about. So looking at these modern day pictures, you can sort of get an idea of why Schiaparelli and Percival Lowell thought they saw things on the surface. Now, Mars also has polar ice caps, very similar to the Earth, except that the ice caps on Mars are made primarily out of what's called dry ice or carbon dioxide ice. So for this Halloween, or in previous Halloweens, if you've ever gone to a party and there was the steaming bowl of punch, that steam is produced by someone dropping a chunk of dry ice in the punch. Okay, so here's a close-up picture of one of the ice caps on Mars. And Mars has seasons like the Earth does. And so in the wintertime, these polar ice caps get larger, and in the summer, they shrink down. And so this series of pictures right here shows how the size of the ice cap grows. So you can see in October 1996, which corresponded to the Martian winter, one of the polar ice caps was bigger than it was in March of 1997. And the reason why those dates don't match up to dates here on Earth is because Mars has a larger orbit, and so it takes it longer to complete one orbit around the sun. So here are some other interesting pictures of Mars. Looking at this picture from the side, you can see that Mars has a very brown atmosphere. It is a thin atmosphere, again, made primarily of carbon dioxide gas. And because Mars is rotating quickly like the Earth does, there are high-speed winds on the surface of Mars. And so you do actually get some sandstorms there. This is a picture of Olympus Mons, which is, again, the largest volcano on Mars and actually the largest volcano anywhere in our solar system. And here are some pictures of other things. One of the things I think is really amazing about looking at Mars is just how similar Mars looks compared to places here on Earth. I mean, this looks like somewhere in southern Arizona, frankly. It looks like you're in the desert. And here you can see in this picture, you can see there are these channels here where there was once water flowing across the surface. So just sharing with you some more pictures of the surface of Mars. Mars even has sand dunes on it, just like we have here on Earth. So Mars is an amazing place, and it's in many ways, very similar to Earth in its appearance. And in this picture right here, these two pictures, you can see how Mars also has sandstorms. And so the picture on the right shows Mars while there's a sandstorm going on. So in many ways, very similar to here on Earth. Now, Mars also has some kind of fun and funky features to it. And so this picture right here shows what some people call the face of Mars. And so if you look at the crater, not crater, but the rock feature, sort of the upper center part of the picture here, you can see that there looks like there is, looks like a face. And so many people have called this the face on Mars. And some people have speculated that maybe there was once aliens there who built this, but that just raises the question, why would aliens on Mars build a rock that looks like our faces as opposed to what maybe their faces were? Now, this is a modern picture of that face on Mars. It was taken several years later. And you can see this rock face actually isn't a face at all. It just looked that way in the previous picture. And the reason why I look that way is just simply because of the lighting on it. The picture on the left was taken when the sun was low in the sky on Mars, and so it cast these shadows, which made it look like it had eyes. But there's lots of other fun shapes on the surface of Mars. Here in this picture, you can see what's called the Happy Face Crater. And so, and there's also lots of other cool things, like this is the upper right picture shows the Butterfly Crater, and the one on the bottom looks like a hot dog in a bun. And this is my favorite crater on Mars. It looks like a heart. So there's lots of cool and fun shapes on the surface of Mars that look like things we're familiar with here on Earth. So let's talk about the history of Mars. So a good question to ask is if Mars once had liquid water on its surface, where did it go? Why did Mars end up as this dry planet? So the answer basically is because Mars is no longer volcanically active. So when Mars was younger and it had molten material inside, that molten material can move around and produce a magnetic field that surrounded the planet called a magnetosphere. Here on Earth, our planet has a magnetosphere, and magnetospheres are important because they protect us from what's called the solar wind. So Mars lost its magnetic field, and the sun's wind ever since has been slowly blowing away the atmosphere of Mars. This drawing right here shows what the magnetic field around the Earth looks like. And what I want you to notice is that this magnetic field protects us from the wind from the sun. So you can imagine the sun is off on the left side of this picture. And as that wind is blowing onto out into space, the Earth's magnetic field protects us from it. So Mars lost its magnetic field when the interior cooled, and so it is no longer protected from the sun's wind. And so we now know that the solar wind has been slowly blowing away Mars's atmosphere, and that's what caused it to lose liquid water. Okay, what about Venus? Now, Venus is also a very interesting planet for a lot of reasons. Venus is often called our sister planet because it's nearly the same size and mass as ours. So it's interesting to compare the history of Earth to that of Venus because these two planets ended up very different from each other. Now, Venus, because it's about the same size as the Earth, has essentially the same amount of volcanic activity. And when we look at the surface of Venus, we see that it is covered almost entirely with lava flows. So whatever craters originally existed on Venus have all pretty much been covered up. We don't see any evidence for plate tectonics on Venus, but this may be because Venus doesn't have any water on the surface. And likewise, there's no erosion on Venus because there's no water or ice, and since Venus is rotating slowly, there's no wind as well. So this picture right here is a topographic map of Venus. The colors correspond to altitude, and so the areas that are brown and red are higher altitude areas than the blue and green. And what you're seeing in this picture are these volcanoes on Venus, and you can see these long stringy lines coming out of them. Those are lava flows that came out of those volcanoes. This is a picture of what one of the volcanoes on Venus looks like, and this picture was taken by a US spacecraft called Magellan that went to Venus back in the 90s. We do see evidence of volcanic activity that looks very similar to what we see here on Earth. In fact, these pictures show what are called pancake domes, and these are areas where there was lava underneath the surface, and after the lava drained out, the surface collapsed and produced these domes. And we see things very similar to this in volcanically active areas on Earth, like in Hawaii. So why did Venus end up the way that it is? Now, one thing to know about Venus is that Venus is the hottest planet in the solar system. It's about 800 degrees Fahrenheit on the surface of Venus. It is hotter than Mercury, even though Mercury is closer to the sun. So why is that? Well, the reason why is because Venus has an atmosphere made almost entirely of carbon dioxide gas. And as you may have learned from climate change here on Earth, carbon dioxide is what's called a greenhouse gas. It's a gas that traps heat. And so what happened on Venus is that its volcanic activity produced all this carbon dioxide gas that went up into its atmosphere, and the gas, it just added more and more and more. And that gas traps in heat and makes the surface of Venus incredibly hot. So why does Venus have this very thick atmosphere made out of carbon dioxide? Well, the big reason is because Venus does not have any water on its surface. It has no oceans like the Earth does. Water can absorb carbon dioxide, and since there's no water on Venus, all the carbon dioxide released by the volcanoes just went up into the atmosphere and stayed there and made it incredibly hot. Now let's compare what happened to Venus to what happened here on Earth. Now on Earth, we have all these different geologic processes, and in particular, I want to talk about plate tectonics. Because of plate tectonics, the surface of the Earth is constantly changing. And these plates move very slowly. They move only about an inch a year. But over the span of millions of years, that's enough time for the surface of the Earth to change dramatically. And so I'm going to just show you some pictures showing here how the plates are moving around on Earth. So what you're seeing in this picture here is it shows the black dashed lines show the lines show the different plates on Earth, and then the pink arrows show what direction they're moving. So if you look near the center of the image, you'll see what's called the Pacific plate, and the pink arrows show that the Pacific plate is moving up and to the left and is moving into Asia. And not only that, it's actually moving underneath what's called the North American plate under Alaska. So the reason why Alaska is so geologically active, the reason why we have volcanoes and earthquakes here, is because the Pacific plate is pushing itself under our state. Now this picture also shows pink dots that correspond to where earthquakes occur. And you can see that the earthquakes that occur in Alaska are predominantly along this place where the Pacific plate is pushing itself under the North American plate. So here's just a close-up on Alaska. You can see this picture here. You can see where the yellow arrow is showing that the Pacific plate, which is the darker area underneath, is pushing itself underneath Alaska. And if we look here at Hawaii, notice that the line of islands here corresponds to the motion of the Pacific plate as well. And in fact, the reason why Hawaii is broken up into a series of islands is that there is a volcanic hotspot, and as the plate moves over it, whenever the volcano erupts, it produces a new island. And so the hotspot is located on the edge of the big island, Hawaii, in the lower right corner, and you'll see where it says volcano there. That is where it is most volcanically active. Now, if we zoom out here, you can see that this chain actually extends for a very large distance. And so you'll notice that there's actually quite a few islands that extend beyond the Hawaiian Islands, but they're not islands because they're completely submerged. The volcano was not able to produce enough lava for it to come above the water. And another interesting thing to look at is, if we zoom out even further, notice that the Hawaiian island chain extends for a distance, and then right near the center of the image, it turns and then goes straight up. So we can actually see how the motion of the Pacific plate has changed over time. We first went there, and then it moved up there. So the surface of the Earth has constantly been changing, and this picture right here shows some of the ways in which the surface of the Earth has changed, going back from a time called the Permian, when nearly all the continents were stuck together in what was known as Pangea, to the present day arrangement of the continents, which is shown in the picture on the very bottom. So the Earth has a much more complicated history than the other planets. And what I want to do now is just talk very briefly about the geologic history of the Earth and talk about some of the major events that's happened. Now, part of the way that we know about the history of the Earth is by looking into ice core samples that are dug out of the ice in the South Pole as well as in the Greenland ice sheet. And with these ice cores, scientists are able to see what the Earth was like a long time ago. And basically the way it works is that at places like Antarctica, every time it snows, it adds another layer of snow and ice onto the continent there. And so by digging a hole down, you can see what was going on in the past by looking at these different layers. And so what you're seeing in this picture right here is an ice core sample. And if you look, you'll see that there is a grayish ring inside there, and that corresponds to when there was a volcanic eruption that dumped ash onto Antarctica. Now, using these cores, scientists are able to figure out a couple things. In particular, they're able to figure out what the temperature was like in the past, and also what the atmosphere was like. And so this plot right here shows what the atmosphere, how much carbon dioxide was in the atmosphere, shown as the blue line, compared to the temperature of the Earth, shown as the red line, over the last 800,000 years or so. And what I want you to notice from this plot is notice that the more carbon dioxide there is in the atmosphere, the warmer the temperature. And this is what we expect because carbon dioxide is, again, a greenhouse gas. It's a gas that traps heat. So when there's more carbon dioxide in the atmosphere, then the Earth is going to be warmer. So the times when the Earth is warmer, these are known as interglacial periods. And times when the Earth is cooler, it is known as an ice age. And looking at this plot, you can see that ice ages occur roughly every 100,000 years or so. And this is something we also see in the geologic record of the Earth. Each layer of dirt here corresponds to a time in the past. The further down you go, the further back in time you're looking. And each one of these red arrows here shows a time when the Earth was during one of its interglacial periods. Okay, so let's talk just very briefly about the history of the Earth. So the Earth formed about 4.5 billion years ago. And for the first 500 million years or so, the surface of the Earth was bombarded by asteroids. And shortly after that, life started to form on the Earth. And there came a time when life evolved into something called cyanobacteria. And at that time, cyanobacteria is a plant life that absorbs carbon dioxide and produces oxygen. So this is the reason why the Earth has an atmosphere made primarily of oxygen and nitrogen rather than carbon dioxide, is that the cyanobacteria that originated on Earth absorbed much of the carbon dioxide and produced oxygen. So the fact that we have oxygen in our Earth's atmosphere is entirely because of life on Earth. Now, other things that I want to point out is there was times in the history of the Earth when it was actually a lot colder than it is now, a time when the Earth was covered almost entirely in snow and ice. And so this is an artist's conception of what's called a snowball Earth, a time when the Earth was so cold that it was nearly covered in snow and ice. And so the first time this happened on the Earth was about 750 million years ago. And after the Earth warmed up beyond that time came what was called the Cambrian Explosion. And this is a time when all these different types of forms of life evolved here on Earth. And then it was about 2 million years ago that the first human-like creatures called hominids evolved on Earth. So one of the things I want to emphasize is that there was times on Earth when it was much colder and it was what's called a snowball Earth. And there was also times when the Earth was much warmer than it is now. So for example, during the Cambrian Explosion, the Earth was considerably warmer than it is now. And so over the time, the surface of the Earth has constantly changed. There's because of plate tectonics, the continents have moved around, and there was times on Earth where it was much colder than it is now, and also times when it was much warmer. And over the last 2 million years or so, we've been in a period where there have been ice ages occurring on the surface of the Earth roughly every 100,000 years. And the last ice age on Earth was about 50,000 years ago and ended only about 10,000 years ago. So if we look back at this plot here, this little yellow area on the right shows a time period called the Holocene. And the Holocene has been basically the last 10,000 years. And so the last 10,000 years is the only time in the history of the Earth where the Earth has been like it is now. And I emphasize this because when we talk about, when we talk about the history of the Earth, the time in which humans have lived on Earth corresponds to about the last 200,000 years, but it's only in the last 10,000 years that the Earth has been warm enough for agriculture. So you may have learned in history class that civilization on the Earth has only been around for about 10,000 years. And that's because that is the time when the Earth warmed up enough that we could start growing the food that we ate. Now, another thing that I'd like to talk about is that the history of the Earth includes many what are called mass extinction events. These are events when nearly all of the life on the Earth was wiped out for one reason or another. And so, for example, there was what's called the Permian Triassic event. This was a time when nearly all of the life forms in the Earth's oceans were wiped out. And there was another event called the KT event, which occurred about 65 million years ago. And this is when an asteroid hit the surface of the Earth and set off a reaction of events which led to the demise of the dinosaurs. And we know this because we can look at the fossil record of the Earth and see times, we can see when exactly the dinosaurs went away. And in the case of the KT event, we actually know where the asteroid hit. It hit off of the Yucatan Peninsula in Mexico. So one thing that I wanted to point out is in this plot here, this shows how the climate of the Earth has changed over the last 800,000 years. Now, if you've been following the news, you know that climate change is occurring here on Earth. And so I just wanted to put into perspective how we're changing the Earth now. So looking at this record here, you can see that the amount of carbon dioxide in the atmosphere has varied up and down over the span of the last 800,000 years. So during the ice ages, the amount of carbon dioxide level dropped down to about 200 parts per million. And then during the interglacial periods, it gets up to a little shy of 300. So what's been happening is by burning fossil fuels, we are adding carbon dioxide to the Earth's atmosphere. And in just the last 100 years or so, we have increased the amount of carbon dioxide in the Earth's atmosphere to over 400 parts per million. So what I want you to see from this plot is that there is this natural range where the amount of carbon dioxide in the Earth's atmosphere was slowly going up and down. And over just the last 100 years or so, we have almost doubled the amount of carbon dioxide in the Earth's atmosphere by using fossil fuels. So a couple of things I'd like for you to take away from my talk today is just that each of the planets has a very different history, in large part because of the size of the planet. So Mercury, because it's small, has never had an atmosphere and has always been a dry, lifeless world. Now, in the case of Venus, because it had no oceans, it became incredibly hot by the addition by all this carbon dioxide that built in its atmosphere from volcanic activity. Mars went the opposite direction. Mars was too cold, and there was once a time when Mars had liquid water, but is no longer suitable for life. And here on Earth, the conditions right now, over the last 10,000 years, have been just right for humans to live as we live now. But as I talked about, there have been many mass extinction events in the history of the Earth. And so in many ways, we're kind of lucky that life has survived and thrived as it has now. Because in the case of both Venus and Mars, we see evidence that these are planets that could, if everything had gone right, could have led to life as well. But in both cases, they did not. Now, other points I'd like to make as far as talking about the Earth's geologic history compared to climate change is that the Earth's climate has changed for natural reasons over the timescales of thousands of millions of years. And there were times when the Earth was much colder and much hotter than now, but we weren't here. So it is true when people say that there's times that the Earth's climate changes naturally, but that's not what's happening right now. It's sort of like if you came back to your house one day and you saw that your house had been burned to the ground and you saw a can of gasoline and a bunch of matches outside your house. And you think, hey, I think someone burned my house to the ground. And then your neighbor said, well, houses burn all the time. How could you know that your house burned because of arson? Well, it's kind of the same thing here. It is true the Earth's climate has always changed, but we know that it's changing now because of human activity, and specifically because we're burning fossil fuels. Now, over the history of Earth, there have been 5 major extinction events that we know of over the last 500 million years. One of them we know was caused by an asteroid impact. The other ones we're not as sure about. But in many of these cases, these major extinction events occurred when there was a change in the Earth's climate. And that is what's basically happening right now, is that the Earth is now in a period called the Holocene, as it has been for the last 10,000 years. But the Earth is now moving into a geologic period called the Anthropocene. And this is a time period where humans are changing the climate. And specifically, we're changing the climate by burning fossil fuels. And so what we're doing is we're changing the Earth's climate in a way that's unhealthy for humans and the plants and animals that we live on. So whenever you hear people talk about how we need to save the Earth, you don't need to worry about the Earth. The Earth is going to be just fine. The Earth has had times where it's been much hotter than it is now, and times when it's been much colder. But what we do need to worry about is ourselves. We need to worry about how we're changing the climate in ways that affect not only humans, but the plants and animals that we rely upon. And we know that right now, because of climate change and other factors, animals are going extinct at a rate 100 times faster than they normally do. So in many ways, we have started the 6th major mass extinction event here on Earth. And so that is why scientists, including myself, are so concerned about climate change. Okay, that was a lot. So I'm going to stop my screen sharing here. And if anyone has any questions they'd like to ask, please feel free to raise your hand, or you can even just unmute your microphone and go ahead and ask your question. Is there anyone here who would like to ask a question? I couldn't have done such a perfect job of explaining everything. I'm sure there's things that I didn't say very well, or maybe questions you have about other things that I
Hello,
could answer
this is
for you.
Darren.
Hi, go ahead.
Hey, I have a question about the flows on the Earth, or not on the Moon, excuse me.
The lava? Mm-hmm.
Yeah, how does the lava flow without an atmosphere?
So the lava flows as long as it's hot enough to stay in a liquid form, but it did rapidly cool. And so when the lava came out, it was a very thin lava, kind of like water, and then it flowed out quickly, and then it cooled off quickly. So you don't actually need an atmosphere to have a flow, but because there was no atmosphere, it did actually cool faster. Did that answer your question? Okay. Any other
Yes,
questions?
it did. Thank you very much.
You're welcome. Any other questions that anyone would like to ask? Yes, no? You're welcome, Mary. I'm glad you enjoyed. All right, well, if there's no other questions that anyone would like to ask, I'd just like to thank you all for tuning in today. I hope you enjoyed the talk. And normally we'd be doing this talk live at the Eagle River Nature Center. So hopefully next time we all do this, we can do it in person. So
Travis, this is Stephanie Whaley. Can you hear me?
Yes, I can hear you, Stephanie. Do you have a question?
I just figured out how to unmute.
Okay.
So you said that there are about 6 major extinction events on planet Earth. And
That we know of, yes.
And you told us about 2 of them. What are the other 4? Are they caused by the same thing?
So we are starting the 6th one right now because of human activity. We know that the KT event was triggered by a large asteroid hitting the Earth.
Yes.
And then the other events we're less sure about. The Permian Triassic event might be related to a supervolcano eruption that released a tremendous amount of carbon dioxide that abruptly changed the atmosphere, made it much warmer.
Okay.
But as you can imagine, as we get further back in time, the geologic evidence becomes less and less clear.
Sure.
So for the other events, we don't know what exactly triggered it, but we do know that all of these mass extinction events are connected to a drastic change in the climate of the Earth. Either it rapidly warmed or rapidly cooled. Now, obviously, this rapid heating or cooling had nothing to do with humans. We weren't even around then. It must have been something else. But it does demonstrate that if we change the climate, if the climate changes quickly, whether it's us doing it or not, it does lead to mass extinction because plants and animals evolve slowly to live in a certain temperature range. And so if that changes abruptly, then they may no longer be able to survive.
Thank you.
You're welcome.
This is very kind of you to share your time with us. And Zoom is a second great way to do it.
Well, it's much more fun to be in person, but
yeah,
it's nice that people can come in, and especially for those of you who are out of state, Zach, down in Texas. I used to live in Texas. I used to live in San Antonio. So it's great to have you be able to come here today and participate. So thank you all for coming today. If there's no other questions, I'd just like to thanks Samantha and the Eagle River Nature Center for inviting me to come and talk with you today.
Thank you so much, Travis. We look forward to hearing you speak again, and hopefully in person.
Okay. Well, thank you all. Have a good night, and I'll look forward to talking with you again sometime soon. Bye, everyone.